Hello everyone, and welcome to our 320 final project. My name is Ben, my partner's name is Feliciano, and we're going to be talking about the active aerodynamic systems of high-performance sports cars. We're going to break down the dynamic features of the system, such as spoilers and splitters, inputs and outputs of the system, methods of control, and control system details, like the PID controller. First, we're going to be talking about a couple of examples, so without further ado, let's go down to the Pagani Huayra and the Lamborghini Huracán Performante.
An example of an active aerodynamic system is in the Pagani Huayra. The Pagani has 4 active stabilizers which will act independently in order to increase the downforce on a specific side of the car. Another example of an active aerodynamic system is in the Lamborghini Huracán. In this system, there are 2 hinges which will open up, allowing airflow to flow through the car, which minimizes drag and increases acceleration of the car. Inversely, it will close off the ports in order to increase the drag when needed, such as turning around corners.
In this block diagram, we'll be discussing how the equations of motion of Newton's second law breaks down the active aerodynamic system. Here we can see that torque is an input, which makes sense because it's directly related to the traction and friction experienced by the tires of the car. So as a car becomes unstable, there's going to be less torque experienced by the wheel. It breaks it down to the necessary downforce to produce the proper friction of the wheels to maintain stability. Since the more downforce there is, there's more normal force being pushed up against the car, therefore increasing friction.
The inputs of the system include speed, steering angle, longitudinal acceleration, lateral acceleration, and yaw rate. Using these inputs, the system will determine which aileron to activate and how far, and which shaft to open up. It will do this in order to determine how much downforce to generate or how much drag to minimize.
Here we have a more detailed block diagram of the PID controller system. It utilizes inputs like torque, yaw rate, and speed to measure, and then measures the error of these values by taking the desired value minus the actual value. And it uses these E of T's in measuring its proportion, P, previous actions as the integral, and predicted future derivative, which stands for PID, actions to compute the response of the overall system.
All in all, an active aerodynamic system is a discrete system that uses Newton's second law. It measures velocity, acceleration, steering angle, and yaw rate in order to stabilize the car and produce efficient turning. The aileron and internal wind redirection are the feedback systems used in order to implement this. The system also uses a PID controller as its main control system.